This talk is the Memory Sinkhole, unleashing an X86 design flaw, allowing for universal privilege escalation, with our speaker, Christopher Domas.
Thanks. All right, good morning, everyone. Thanks for coming out. My name is Christopher Domas. I'm a cybersecurity researcher at a group called the Battelle Memorial Institute. It's a pretty cool place to work. Gives me a chance to do a lot of research into the fringe areas of cybersecurity that I wouldn't otherwise get to see. But what I wanted to talk to you about today is something I've been tinkering with in my free time for the last couple of months. It's actually an X86 architectural vulnerability that allows privilege escalation. And it's been hidden on these processors for the last 20 years without anybody noticing it. What it effectively does is open up an entirely new class of exploits on these processors. And I want to talk about exactly how that's going to work. But first, I want to give a demonstration in order to sort of frame what we're going to see today. So this demonstration is a little bit risky. So instead of doing this on my actual presentation laptop, I've got this little netbook over here. I love doing this deep vulnerability research on these netbooks because I can brick these things all day long and just not feel bad about it. And just in case something does go very bad, I've got an entire stack of backups here, so we should be prepared. So I'm SSH'd into this netbook. That's the prompt that we see here. And I'm just SSH'd in as some boring, unprivileged user who can do boring, unprivileged things. But one of the things a boring, unprivileged user can do is they can run boring, unprivileged programs. So I've got this simple little C program here that doesn't really do anything interesting. All it does is create a couple of 64-bit variables. It's got this sort of kludginess here that I'll fix later on. This ensures that the process is going to be scheduled on core 0 of the processor. Right now, this exploit's only going to work on core 0. I can fix that later. But then we do something very, very simple. We just sit in a loop for a couple million iterations, and all we do in this loop is write the 64-bit value out to memory, read it back in from memory into the processor registers, and then write that back out to memory again. And we do that over and over and over again. So this isn't row hammer. This is literally just reading a 64-bit value into the processor registers for a very, very long time. And after that's done, we're going to exec bin shell, hoping that maybe we cause something to happen by using this magic 64-bit number. So I'm going to go ahead and compile this simple C program here. And one more time before I run this, double check who I am. I am user right now. Then we're going to go ahead and run this little C program here, and hopefully maybe something will actually happen. So we run this and it sits in that loop, and it didn't work. We still have that $, which means if we check who I am, I'm still user. So of course it didn't work. You can't escalate privileges by loading a 64-bit number into the processor registers. That's kind of silly. But maybe you can. Maybe if we find the right 64-bit number, we can do that. So I'm going to change that last 3 in the 64-bit number. It's going to become a 4 instead. And we're going to retry this attack. We'll recompile the program one more time, verify that we're just user, and run the program. And all of a sudden, something changed. So we're going to spend the rest of the hour figuring out how this thing works. But I got to warn you, it's flashier than it actually seems. There is absolutely nothing special about that 64-bit value. If you run this exact same code on your computers, absolutely nothing will happen, exactly as you would expect. All that 64-bit number really was a signal to something running much, much deeper on the processor. It was something running so deep that our process couldn't see it. In fact, even the kernel running in ring 0 couldn't see the piece of code that just gave us that root access. In fact, you could tear this system apart to the last piece and do a forensic analysis on here and not be able to see the piece of code that just gave us that root access. So what we're really going to find out is exactly how to get something running so deeply on the processor that nothing else can see it there. What we're going to see today is an architectural solution for ring -2 privilege escalation. So in order to understand how this works, we need a little bit of background information on the X86 privilege model. So X86 divides privilege into different rings. So at the top is ring 3, where we really can't do anything useful. That's where all our userland code runs. Inside of ring 3, just doing boring, uninteresting things. We've got ring 2 and ring 1 below that. Nobody really uses those anymore. But ring 0 is where the real magic happens, where the kernel lives. That's where we can finally start doing some interesting things on the processor. And usually, if you want to do something really interesting in an exploit, you try to go from ring 3 down to ring 0. But it doesn't stop there. It goes much, much deeper than that. Over the course of evolution of the x86 processor, we sort of found out that some things are so important that ring 0 shouldn't have access to them. So we created additional levels of privilege deeper on the processor. So we invented this ring -1, which is more commonly known as simply the hypervisor. But as we found out eventually, some things are still so important that even the hypervisor shouldn't be able to access it. So we created another level on the processor, what we call ring -2, or system management mode. So system management mode started out simply enough. It was just, what if we have this mode of execution that's invisible to the operating system? Why would we want something like that? Well, originally, it was pretty simple. We just wanted to be able to do power management without the operating system having to worry about it. That was a simple goal for system management mode. But it evolved from there. Over the course of time, system management mode sort of became this dumping grounds for all these miscellaneous things that we didn't want the operating system to have to worry about. And then all of a sudden came a big one. We dumped platform security into system management mode. And why not? Platform security is really, really important. And ring 0 could be compromised. If we put platform security into ring -2, all of a sudden we don't have to worry about ring 0 compromises anymore. But this really opened up a whole Pandora's box for what system management mode can do. It's now in charge of an alarming number of very important things on the processor, like cryptographically authenticated variables, signature verifications, hardware locks, TPM communications. It controls a platform lockbox on that system, and it's actually the interface to the root of trust on the system, because system management mode alone can modify the very first instruction that the processor will ever execute when it turns on. So basically what we've seen over the evolution of SMM is that whenever we had anything that was so important that we didn't want the kernel to screw it up, or so secret that it needed to be hidden from the OS and DMA accesses, or so sensitive that it should never be touched by anyone, we just toss that into system management mode. So on modern processors, this is really what our privilege model looks like. At the highest level, least privilege is just our ring 3 code, and sitting just below ring 3 is ring 0, where the kernel executes. But much deeper than ring 0 is the hypervisor, and there's a chasm that separates the hypervisor from system management mode in ring -2. So ultimately, ring -2 is what's really in control of the processor. So if you think that you own a system when you get down to ring 0, you're really not even close, because there are layers and layers of separation between ring 0 and the actual processors. On modern systems, ring 0 is simply not in control. Ring -2 is what controls the hardware, the firmware, and all the most critical security checks. So if we want to do something interesting, we need to find a way to get deeper than ring 0. But in order to figure out how to do that, we need to understand how the privilege model for SMM works. How can SMM be something invisible to the operating system? How can ring 0 not see something sitting in memory? Well, the idea behind system management mode is that it's going to execute from a special region of memory called system management RAM, or SMRAM. And that region of memory is only going to be accessible to SMM code. So the idea is that the processor will receive what's called a system management interrupt, an SMI. That's going to switch the processor over to system management mode, and that's going to unlock SMRAM. System management mode is going to execute from SMRAM, and when it's done, it's going to issue the resume instruction, which is going to leave system management mode and relock SMRAM. So with this model, system management RAM is only ever visible to SMM code. That's how we hide it from ring 0. So if you're sitting in ring 0 and you try to read from SMRAM, so on the specific system I was looking at, SMRAM started at 1FF.8 megabytes. If we try to read from that address from ring 0, we're just going to get a bunch of garbage, a bunch of Fs in this case. We can't actually see what's there. But how does that work? How is it possible that ring 0 can't see memory that's physically on the system? Well, that's the memory controller hub's job. Its job is to separate SMRAM from ring 0, and it's ultimately in charge of enforcing SMM security. So this is sort of the layout that we have for SMM security. We've got the processor on the left and the memory controller hub sitting in between the processor and memory, and SMRAM sitting somewhere in memory. So if we're in SMM and we try to read from a memory address inside of SMRAM, the memory controller hub looks at that address, sees that it's in SMRAM, it looks at what mode we're in, it sees that we're in SMM, so it allows us to access that memory. It returns to us some real values. On the other hand, if we were in ring 0 and we tried to issue that exact same instruction, that address goes over to the memory controller hub. The memory controller hub says, no, you're not in SMM. You can't access this memory. Here's a bunch of Fs instead. So that's sort of how SMM security is designed, but who's to say we can't modify the memory controller hub? Why can't we just go around this? I mean, we're ring 0 code after all. We should be able to set this stuff up. Turns out that there are layers and layers of protections built around SMRAM to keep us from ever seeing what's inside of that memory, from ever modifying system management mode code. So we've got ways to configure CSEG, HSEG, TSEG, the different regions of SMRAM. We've got ways to lock SMRAM down. We've got ways to lock the locks down. We've got ways to enforce cache coherency on the processor. We've got ways of preventing remapping the memory controller hub configuration. We have locks and locks and locks and locks and locks on this processor, keeping us out of system management RAM. And this thing is better protected than ring 0 is, and it is a daunting task to try to get past all of these things. So a lot of these locks, well, some of these locks are on the processor itself, but most of these locks exist in the memory controller hub. So as far as how we can get around these things, there's a lot of really, really cool research going on right now and how to circumvent these protections in order to dive into ring -2 code. So there's ways of attacking the fringes of the memory controller hub, ways of exploiting misconfigurations in the firmware and SMM code. So if you're interested in that kind of thing, you should check out the research from Legbacor and ITL and ATR. Some really cool stuff going on here. I want to present something a little bit different because there is a way to simultaneously circumvent every single one of these protections, and it's built into the architecture itself. In order to understand how that works, we need to step back in time and look at something completely unrelated to system management mode. A while back, some 20 years ago, we had something called the local APIC. So the local APIC in the X86 architecture is in charge of receiving interrupt events from things happening on that system and sending those over to the processor. And it used to be that the local APIC was a physically separate chip on the chipset, and it sent things over to the processor. But that was sort of an inefficient design. So 20-some years ago, Intel moved the local APIC onto the processor itself. It moved the local APIC into the actual silicon that the processor was using. And that had a lot of benefits. It's way more efficient and cheaper to manufacture things this way. And it also opened up a unique opportunity. We no longer have to use I/O instructions to communicate with the local APIC. We can now use MMIO, memory mapped I/O, for communicating with the local APIC, which means we can configure and communicate with the APIC way, way faster than we ever would have been able to before. So with the P5 generation of microarchitectures, Intel reserved this region of memory, this 4 kilobyte region starting at FEE megabytes. And they said whenever you try to access this region of memory, instead of being sent out of the processor, that memory address is going to be accepted by the local APIC. And you're going to be accessing the APIC registers instead. So for example, let's say you wanted to quickly access APIC register 280. What you would really do is issue what looks like a memory read instruction accessing 280 offset from FEE megabytes. You'd move that into one of your registers. So the APIC is going to catch that memory access and then give you back one of its own registers. This caused a problem for Intel. Intel doesn't like to break things when they release a new processor, and that makes sense. But this broke something, this model. Namely, there were some old legacy systems that were already using that memory range for something else. If they then drop in one of these new processors that expects that memory range to go to the APIC, that's going to break things. So they could have fixed their stuff, but instead Intel decided to fix their processors instead. So with the P6 generation of microarchitectures, they changed things a little bit. So if you dig out the 1997 version of the Intel Software Developer Manual, you'll find this blurb buried in there. The P6 family of processors permit the starting address of the APIC registers to be relocated from FEE megabytes to another physical address. This extension of the APIC architecture is provided to help resolve conflicts with the memory maps of existing systems. So that's really, so this is how that's going to work. In its default configuration, the APIC accepts accesses within this memory range. So if we were to issue a memory request within that memory range, the APIC is going to catch that first, and it's going to give us back one of its registers, in this case, register 280. On the other hand, if we tried to access something just 1 megabyte below that, that looks similar, that's not in the APIC range. The APIC is going to look at that and be like, well, that's not in my range, so it's going to send that out on the system bus, and you're actually going to fetch RAM from memory instead. But with this new addition to the P6 generation of microarchitectures, they let us move where the APIC is. So we can issue a couple of assembly instructions and a write MSR instruction in order to change where the APIC window is located. So now I just moved the APIC so that it's located at FED megabytes instead of FEE megabytes. If I issue those same exact two instructions, now FEE goes out onto the system bus and fetches from RAM, and FED is accepted by the APIC so that we access an APIC register. So seems trivial. It's a vestigial feature to fix some things that occurred a long time ago. It's largely been forgotten. Nobody really uses this anymore. In fact, the software manuals almost universally assume that the APICs are located at FEE megabytes. It's really just a forgotten patch to fix a forgotten problem on some tiny number of legacy systems some 20 years ago. But incidentally, this opens up an incredible vulnerability on an entirely unrelated piece of the processor today. So we can actually use this relocatable APIC feature from 20 years ago to attack modern system management mode code. And here's how we would do that. If we look at the standard configuration for the processor, if we're sitting in ring 0 and we try to read something out of SMRAM, that address is going to be sent out to the memory controller hub. And the memory controller hub is going to say, you're not an SMM, you can't access SMRAM. It's going to give us back a bunch of Fs. Can't do anything. On the other hand, if we did that exact same thing from SMM, that address is going to be sent out to the memory controller hub. It's going to allow us to access SMRAM. It's going to give us back an actual value in that situation. But what if we're in ring 0 code and we move the APIC? We put the APIC so that it overlaps the SMRAM region instead. All of a sudden, we've changed the view of our memory. So from ring 0, we issue that exact same instruction that we just tried to issue, where before we got back a bunch of Fs. Now that address never makes it out of the processor. The APIC accepts that address now, and it gives us back one of its registers instead. That's not really interesting. It doesn't matter if we can modify our view of memory in ring 0. The interesting part is this allows us to modify SMM's view of memory. So now if SMM tries to fetch a value from SMRAM, instead of getting what it actually expected to see, the APIC's going to grab that memory access and give us back a register instead. So the MCH in this situation never actually received the memory request, meaning that the primary enforcer of ring -2 security has just been removed from the picture. So through this legacy APIC-based feature, ring 0 can manipulate the APIC MMIO range and intercept ring -2 accesses to SMRAM. So how could we actually use this to attack ring -2 from ring 0 and try to infiltrate this most privileged realm of execution on the processor? Well, the concept is that SMRAM sort of acts as a safe haven for SMM code. It's where SMM lives. It's in SMRAM. And as long as SMM code stays inside of SMRAM, we can never see it from ring 0. We can't touch it. We can't modify it in any way. But if we could get SMM to step outside of its hiding spot, if we could get it to leave SMRAM and go into normal memory, then we could hijack its execution and gain SMM privileges for ourselves. So the first version of this attack is really pretty straightforward. The idea is to move the APIC over SMRAM, let the system switch over to system management mode. It's going to fault because it's reading a bunch of data that it didn't expect to have there. And when it faults, it's going to try to figure out how to handle that exception. It's going to look up an exception handler in the interrupt descriptor table, and that handler is under our control. Our handler is then going to execute with SMM context. So pretty simple idea for an attack. Unfortunately, it fails. There's an undocumented security feature on these processors. When this processor switches over to system management mode, it zeroes out the IDTR limit field, effectively disabling interrupt handling. When that happens, if you trigger an exception in system management mode, the system does what we call triple faulting. It's essentially a reset of the system. So if we try this attack from ring 0, we can triple fault the system in system management mode, but what good does it do us to simply reset the system from ring 0? We could have done that anyways. So we've got to find a much more elaborate version of this attack. So here's what we're going to do instead. We're going to overlay that APIC MMIO range at the SMI entry point. So when the system first switches over to system management mode, the very first thing it tries to execute, we're going to put the APIC right over that location. Then we're going to load up our APIC with a payload that we want the processor to be executing inside of system management mode. We're going to trigger an SMI, a system management interrupt, to switch the system over to system management mode, and that's going to allow us to hijack execution when SMM begins executing our payload directly out of the APIC. So that looks something like this. In a normal situation, when the processor receives a system management interrupt, it tries to fetch the first SMI or system management mode instruction from a fixed address. It sends that address out to the MCH. The MCH retrieves that instruction from SMRAM, gives it back to the processor to execute. Simple enough. But if in ring 0, we decided to move the APIC range so that it exactly overlapped the SMI entry point, we've all of a sudden taken control of which instructions the processor is going to be fetching when it switches to system management mode. So from ring 0, then, we can trigger an SMI by writing to the B2 ports, which is going to transition the processor to system management mode. Only now, when it tries to fetch the first SMM instruction, it's going to fetch it out of the APIC registers instead of out of SMRAM. So APIC is going to return one of its registers, and the processor is going to try to execute that as if it was an instruction. So if we could store shellcode in the APIC registers, then we could gain control of the processor within SMM. It turns out to be really, really hard to do. The challenge is that the APIC registers have to be 4K aligned, meaning that we have no real leeway in how we place this APIC memory window. We have to put it exactly at the SMI entry point. We've got 4096 bytes available inside of the APIC that we can use for our shellcode. Unfortunately for us, only those bytes are actually writable, and only a few bits of each of those bytes are writable. That's not a lot of control over this shellcode. Complicating matters, this is actually an invalid instruction. So the SMM is going to begin executing these registers from the top, but when it hits this invalid instruction, that's what we call triple faulting. It's going to reset the system. Our attack's over at that point. We have control over exactly 17 bits before that happens. So our black registers in this diagram are largely hardwired to 0. So if we try to disassemble 0000 as an assembly instruction, that's just an add instruction. It doesn't do anything useful, but it's also not harmful, which means the attack can continue. So this is what our shellcode ends up looking like. It's mostly just a bunch of add instructions that we have no control over, and every once in a while a couple of bits that we can actually modify where we have to try to do something useful. Unfortunately, eventually we're going to hit this region where we can't change it, and that's not a valid instruction. It's going to trigger a fault and reset the system. We need to make something useful happen before that occurs. So these are the exact APIC registers we have control over in this region. And when I say control, I mean that word very loosely, because some of these registers we can't actually directly write to. They're actually pulled from other things on the processor and on the system. So getting those registers set to the right value involves setting the system up to a very specific state just so that those are read as the instruction that we want them to be. Turns out this is pretty hard to work with. If you tinker with these registers for a really, really long time, try to make them into something useful, what you're eventually going to find is that the best instructions you can possibly get into these registers do nothing. But the bad instructions, the ones you don't want to use, crash the system. So you end up wasting most of your 17 bits just trying to keep the system alive, trying to keep it from resetting when it's executing out of the APIC. But if you do that just right, you can get it to not crash by the time it hits your last byte. So that last byte is our last chance. That's the spurious interrupt vector register inside of the APIC. If you look up the documentation on this, it'll tell you that the low nibble, bits 0 through 3, are hardwired to 1. The high nibble is actually writable. That means if we're trying to pick an instruction to place into that register, it's got to end in Fs. That gives us 4 bits left to try to take control of the most privileged mode of execution on the processor. So we need to figure out what instruction could we possibly put into the spurious interrupt vector to make this thing do something useful before the system crashes. If you consult an opcode map, our choices are pretty slim. We've got prefix bytes that don't do anything, some ways of modifying the stack, a bunch of instructions that shouldn't even exist in this architecture. None of these do anything for us. But all of a sudden, right about when we're out of possible opcodes to place into that register, we hit a small miracle, an IRET instruction. That's a return from interrupt routine. And IRET's going to pop a return value off the top of the stack and jump to that address. That'll give us a way to escape this horrible APIC and jump to some code that we actually have reasonable control over. So by placing an IRET instruction into that spurious interrupt vector register and then configuring the stack to support this IRET instruction, we could then remap the APIC, trigger an SMI, and take control of the processor. So this is what our APIC payload attack looks like. We set up that IRET instruction, set up a stack, set up a payload to jump to, remap the APIC, and then trigger an SMI. This is really, really cool. I was really excited to find this, so I launched that payload out of processor, and it doesn't work. That was depressing. I spent 40 hours debugging this thing, trying to figure out why it doesn't work. And it turns out that instruction fetches actually bypass the APIC window. That's not the kind of thing they document. Nobody was ever supposed to try to execute code out of the APIC registers. It turns out only data fetches actually hit that window. This attack is useless at this point. It just got a whole lot harder. So I was kind of despairing at this point. This was a real vulnerability. I could influence the view of SMRAM, but it doesn't do us any good if we can't actually take control of the system. But I tried to reason about it and started thinking, well, we can't execute from the APIC. We don't have control of the instructions. We're going to have to take control of SMM through data accesses alone. And suddenly that started to sound like something rather familiar. There's other common situations where we don't have control over instructions, but we do have control over data, and we try to get the system to do something useful. So maybe we could do something like APIC wrapping in order to circumvent this execution limitations. We can sort of do that, but it turns out to be way more difficult than I imagined. Because if we fault the system resets, the attack is over. SMRAM's invisible. We can't even see the thing we're trying to attack. 99.5% of the APIC bits are hardwired to 0. We have no control over the data that we're using in this attack. And the APIC has to be 4K aligned, and it's 4K large. That makes it really unwieldy. So this is more like blind wrapping with this enormous unwieldy payload of zeros. But if we're open-minded, we can maybe make this work. So that's the memory sinkhole attack that we're going to see. Essentially, from ring 0, by moving that APIC, we can sinkhole a single page of ring -2 memory. So that reads from that memory returns 0 because most of those registers are wired to 0, and writes are completely lost. Since those registers are hardwired, any writes are simply discarded. So that's the sinkhole effect for this SMM attack. The challenge then is, how do we attack code when our only control is the ability to disable a page of memory? That's not a whole lot of control, but if we use our imagination, maybe we can find some ways to do this. But our ultimate goal needs to be to cover as many systems as we possibly can. So in order to do that, we need to understand a little bit about where SMM code comes from. SMM code is actually installed by your system firmware. So if we want to make a very broad attack, we need to understand the firmware ecosystem a little bit. So firmware starts with Intel. Intel writes what they call the EFI template code. It's sort of a skeleton firmware for other people to adapt from. And they give that template code to the independent BIOS vendors, the IBVs. The IBVs add their own modifications to the template code and sell it to the OEMs, things like HP and Dell. They add their own modifications to the template code and then adapt it for each of the individual models of computers that they sell. So you end up with really diverse system management mode code by the time you get down to the individual systems. So we could try to attack that OEM code, the stuff they added, but even if you find an exploit in that code, it's really only going to affect one system. If we attack the code that the IBVs wrote, we'd do a little bit better, but if we really want a universal attack, we have to go after that template code that everybody is using. It's hard to attack, but one exploit will allow you to attack almost any system out there. So it just so happens that the EFI template code is actually responsible for the SMM entry points. And that's what that entry point looks like. This is a little bit hard to decipher if you're not familiar with the SMM execution environment. But this is the entry point for SMM on nearly every modern system because it comes from that template code. So execution in SMM starts in what we colloquially called unreal mode. And it's executing from high memory, which, as it turns out, is a really complicated environment to try to write code for. So the very first thing that this SMM handler tries to do is it tries to set up some kind of reasonable execution environment for the rest of the SMM code. And it's going to do that by building up segment descriptors, transitioning the processor to protected mode, and then transitioning the processor to long mode. And the pieces of this that are really important for that process are these little pieces right here. So with a little work, we can reverse engineer this and understand exactly how it's operating. The very first thing this SMM code is going to try to do is it's going to try to set up a GDT descriptor. That's a global descriptor table, which is basically going to define the memory mappings to use in the rest of SMM. So the first thing it does for setting up this GDT descriptor is it reads the size of the GDT out of memory and stores that into the descriptor. Then it reads the location of the GDT out of memory and stores that into the descriptor. It's going to use a little self-modifying code here. We've got an upcoming far jump. That far jump is going to transition us from 16-bit protected mode to 32-bit protected mode. It's going to use self-modifying code to write out a selector into this far jump. It writes out selector 10 for that. And then some more self-modifying code to write out the offset that it's going to jump to for this far jump. Finally, we hit this far jump. What the far jump does is it looks at the global descriptor table, looks up its location in memory, and then accesses that global descriptor table. It then moves to offset 10 in the global descriptor table to figure out which segment of memory it's about to be jumping to. So segment 2 happens to be at offset 10 inside of this table. It fetches information about that segment, and then jumps to this offset within that segment. So that's how execution is supposed to work. And if we look at that code in a little bit more depth, what you're going to find is that all of that information that it loaded out of memory is being read from one large structure called the DSC structure. The template SMM handler uses this single structure for storing all of its most critical environment information, things like the global descriptor table information, the segment selector information, the memory mappings that it's going to use inside of system management mode are all stored inside of this one structure. So sinkholing this structure that has all the most important information for SMM would be devastating for the processor. So I figured, let's see what happens when we do that. So from ring 0, we try to sinkhole that DSC structure by moving the APIC over its location and then triggering an SMI to transition the system to system management mode. We can watch what exactly happens on this system. We don't have control over the processor anymore at that point. It switches to system management mode, and then it's out of our hands. Any exception is going to reset the system, but maybe it'll do something that'll let us hijack execution before it resets. So these are the pieces of memory out of that same region that we just looked at. These are now the memory accesses that are going to be sinkholed by our attack. Each of these is going to read a 0 out of the APIC registers instead of what it intended to read out of SMRAM. So once again, it's going to try to set up a global descriptor table descriptor in order to define its memory mappings. And the very first thing it's going to try to do is it's going to try to load up the size of that global descriptor table. But it accesses the memory sinkhole reading a 0 for the size. That would kill our attack right there. If you have a 0 size for your descriptor table, that means you have no memory mappings on the system. It's going to triple fault and reset. But we've got this miraculous instruction in here that just happens to save us. They decrement that size. So instead of being 0, it becomes FFFF, the largest possible descriptor table size we could possibly have. And then they store that into the global descriptor table register. The next thing they need to figure out is where's the global descriptor table located. Again, they read that out of the sinkhole and then write that into this GDT descriptor. And again, it's miscalculated now as being at address 0. So we just successfully tainted the entire global descriptor table descriptor that they constructed here. That's going to help us a lot in some upcoming code. This little chunk's not especially relevant. They end up doing some more self-modifying code for an upcoming instruction. Because they're reading that information out of the sinkhole, they end up corrupting that upcoming instruction. So if we get this far, if we get down here past this jump, the system's going to triple fault because of this corruption and reset, and our attack will be over. Fortunately, we never make it that far. So once again, they do some self-modifying code. They write out that selector 10 into the upcoming far jump. They try to set up the offset to use for that far jump. That's going to be miscalculated again because of the sinkhole, so we managed to taint that far jump value as well. So when it hits the far jump now, it's going to try to figure out where's the global descriptor table located, what memory mappings am I using, what segment of memory am I going to. So it's going to fetch that global descriptor table from address 0. Address 0 is now outside of SMRAM. That's something we have control over from ring 0. So we successfully got it to fetch some data that we can actually influence at this point. So it's going to look up a global descriptor table at address 0. And it's going to move to offset 10 inside of that table and read a segment selector out of that offset. So the segment selector now, since this is in a GDT that we control, is also a selector we control. That means we control which memory mappings it's going to be using. The memory segment it's about to jump to is now under our control. It's going to add its offset to that memory segment base, and it's going to jump to that region. So that far jump caused SMM to load a protected mode memory mapping from the GDT under our control. And if we were to preemptively configure a malicious global descriptor table and place it right at address 0, then we could control exactly where this jump is about to go. We could force it to jump outside of SMRAM to code that we control to hijack the processor in ring -2. So this is what our payload looks like in this situation. And it seems a little bit complex, but after pre-processing, it boils down to just these instructions. Flushing the cache, setting up a descriptor entry in low memory for it to use, and then moving the APIC registers to sinkhole that DSC structure, and then simply looping in place, simply waiting for a periodic SMI to transition the system to system management mode so that we can take control of the processor. When we do that, we fire it at the processor, we wait, and it works this time around. So I was extremely ecstatic to see that this thing worked, because with 8 lines of code, we now just successfully exploited a huge number of features on this processor. We exploit hardware remappings, descriptor cache configurations, instruction and data cache properties. The processor is going to go through 4 execution modes and 4 different memory models before it actually hits that far jump that we tainted and jumps to code under our control, so that we can successfully infiltrate the most privileged mode of execution on the X86 processor. And the coolest thing about this whole thing is that template SMI handler had no vulnerability in it. There was absolutely nothing wrong with that code. We managed to attack it through this flaw in the X86 architecture. And like I mentioned earlier, this opens up an entirely new class of exploits against ring -2. We can start looking for other things that we could apply the sinkhole against. So for example, this is the firmware that I pulled off of the MacBook that I've got up here for this demonstration. This is how the Mac handles interrupts in system management mode. They have this table of function pointers over here. Then they're going to use this call instruction to call into one of these function pointers. If we were to sinkhole this table of function pointers, that call instruction is going to fetch a 0 as the address that it's supposed to branch to, forcing SMM to jump outside of SMRAM to where we can hijack it. Alternatively, the SMM stack is another fantastic place to apply the sinkhole. All SMM code is going to try to set up a stack to use when it's executing inside of system management mode. So if we were to apply the sinkhole over the stack, then every call instruction inside of SMM is going to try to push a return address onto the stack. That return address is going to get consumed by the sinkhole and just completely lost. But when it issues a return instruction, it's going to try to pop a return address off of the stack. It's going to read a 0 out of the sinkhole and branch to address 0 under our control. So there are just a tremendous number of things we can apply this to. It's really whatever you can imagine. So the question then is, what do we actually do with this capability? Okay, we've got ring -2 control. How do we use that? Well, we can unlock hardware that wasn't available to us in ring 0. We can disable the cryptographic checks on the system. We could brick the system if we wanted to. Since system management mode is in charge of thermal regulation on many systems, we could just halt and catch fire. We could open the lockbox on the system, or we could just install a really, really nasty rootkit. So that's the route I took. The normal demonstration for when you gain system management mode access on a system is to simply brick the system. And it's a really cool demonstration, but it's not necessarily the most practical attack. I thought it'd be way, way more interesting to actually install a system management mode rootkit using the memory sinkhole attack. So that's what we do here. We deploy this rootkit through the memory sinkhole. Once the rootkit has control in system management mode, that means it can preempt the hypervisor. It can periodically intercept ring 0 code. It can filter ring 0 IO accesses. It can modify any memory on that system. It can escalate process privilege levels. And it can do all of this completely invisible to the operating system, to ring 0, to antivirus technology, and to the hypervisor. Our rootkit at this point, once it's placed in SMRAM, is entirely undetectable on that system. So for this demonstration, I hacked together some code created by this guy, Crash, who made a really, really cool, robust SMM rootkit. So I adapted some of his code for this demonstration. What we do is we signal that rootkit via some magic 64-bit number in user land. When the SMM rootkit sees that magic 64-bit number, it knows that some process is secretly requesting to be escalated in its privileges. So the SMM rootkit then parses that process's page tables, locates the process credentials, and gives it root access to the system. So if we revisit the attack that we illustrated early on, the way this really worked so we have this attack driver code. The attack driver is what's in charge of using the memory sinkhole exploit in order to actually install a rootkit onto the processor. So the attack driver is actually not too complex. It simply installs a hook into low memory. That's what SMM's accidentally going to branch to. Copies the actual rootkit that we want to use into memory for later reference. And then it has some inline assembly here to actually apply the sinkhole attack. So in this specific situation, I was tinkering with using the sinkhole attack against the SMM stack. So we sinkhole their stack, forcing them to branch to address 0, where our hook will take control and install the rootkit into system management RAM. Our rootkit itself, like I said, adapted from a Crash's source code. Also not especially complicated. All it's going to be doing is reading a couple of register values out of what's called the state save map. Basically, it's going to look at what process it interrupted. And if it sees these magic 64-bit values in those registers, then it knows that a process is secretly requesting privilege escalation. So it calls the privilege escalation function for that process. The privilege escalation function parses that process's page tables locates its credentials, and assigns it root privileges here. So going back to the actual escalation attack, when we run the escalation attack, all it's really doing is loading those couple of 32-bit values into the registers to signal to the rootkit running on the system now. If we remember to actually install the rootkit. So when we run the sinkhole script, it'll use that driver to install our rootkit into system management mode where it can no longer be seen. So that now, when we run our escalate process, we surreptitiously gain access to root. So the impact of this is fairly large. We simultaneously just circumvented every single ring -2 protection in place on this processor. And the mitigations don't look great. Could we do a firmware update to fix this kind of thing? Maybe move the APIC back to the proper location inside of the system management mode code. You can try that. The problem is by the time you're able to do that, you have probably already been sinkholed by the attack. So it doesn't really work very well. Could you do a microcode update? Probably not. This is too deeply ingrained in the processor. It's not something you can easily reconfigure. Really, this is unpatchable. The only real mitigation to this attack is to build new processors. Unfortunately for me, that's exactly what Intel did. Somebody at Intel discovered this shortly before I did, and this problem is fixed on their latest generations of processors. So starting with Sandy Bridge and Atom 2013 processors, what they have are some undocumented internal checks against what are called the system management range registers when you try to relocate the APIC. And if you try to put the APIC over SMRAM, they're going to block that from happening. The good news from an attacker's perspective is that still requires the SMRRs to be properly configured, which an alarming number of systems are still not doing. As far as AMD goes, I haven't had enough time to thoroughly research AMD. I'm still analyzing that, and I'll keep people posted on what I find as far as AMD is concerned. What I can tell you for now is AMD doesn't have these SMRR registers. They never needed them for the same reason that Intel did. So this fix on Intel processors won't work on AMD processors. On top of that, AMD tends to document their stuff really, really well, which is actually incredibly helpful from an attacker's point of view. So AMD actually has buried in their developer manuals a blurb stating that the APIC window takes precedence over the SMRAM window, meaning that the APIC attack should work on AMD processors. And I don't know for certain, but I suspect these are very vulnerable to this attack. But these mitigations only work if every single one of these other security mechanisms is properly configured. And even when that's the case, there are hundreds of millions of processors out there right now in which this can't be fixed. So I'm working on getting a CVE number from this. If you're interested in Intel's perspective on the problem and what they're doing to mitigate the issue, you can go to intel.com/security and see their write-up right now. So I coordinated this disclosure with Intel. I got to tell you, they have been fantastic to work with. They were really interested in keeping their processors secure. They instantly started working on mitigations wherever it was architecturally feasible. They're working on their most recently vulnerable processors and working their way backwards. It will take a little bit of time for their updates to trickle down. So in the meantime, just be careful. So looking forward for the future of this attack, as far as I know, this is actually only the second architectural privilege escalation vulnerability on the X86 processor. That's behind the original SMM cache poisoning attack discovered by the Flaw and Invisible Things a couple years back. So there have been exploits against the chipset configuration, vulnerabilities in the firmware and software. We've even had DRAM corruption errors, but the processor itself has actually been surprisingly resilient to attack throughout its long history. But X86 is an immensely complex architecture with 40 years of evolution behind it. So I think what we're going to keep on finding is that there are a multitude of pieces that are individually secure but maybe collectively vulnerable, as was this case where the SMM was secure, the APIC was secure, but when you combine those two things, it introduced an interesting vulnerability. So I really think we're just beginning to scratch the surface in terms of these style of attacks. So a lot of people went into helping this work either directly or indirectly. So I wanted to make sure to acknowledge my coworker, Scott Lee, a bunch of fantastic researchers in this field, the teams at Intel and Crash who created that SMM Rootkit, which I was able to deploy with this attack. So if you're interested in looking at some proof of concept code for this in a little bit more depth, you can check out my GitHub page. You can also follow me on Twitter for more updates on this attack as I do more research. It's XOR EAX, 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 or you can email me at the same address. And I've got a few minutes left. So I wanted to diverge a little bit and talk about a side project of mine. Since I'm at Black Hat and I'm talking about weird x86 things, I also thought it'd be a good opportunity to release another weird x86 project I've been working on. So if you saw me speak at Recon a couple months ago, I talked about this weird x86 fact in that the move instruction is itself Turing complete. So what that meant from our perspective is that you could write entire programs using only the move instruction, which was really cool. And as a proof of concept for that, I made this compiler that compiled code from this really, really awful language called brain yuck into only move instructions. So we could actually run move-only programs, which was neat, but writing code like this isn't the most practical thing in the world. So I promised an alteration to that compiler. So today, in the next hour, if you check out the GitHub page, I'll post what I think is the world's first single instruction C compiler. So it's got a little shell script there. After you download the source code, it'll help you build everything. And then it'll help you actually run through this to see how the single instruction C compiler actually works. So I call this thing the Mofuscator. When you do a git clone, you'll get this check script. And it's going to download an open source implementation of the AES algorithm. It's then going to compile it with the Mofuscator and dump out the assembly results. So what you see is just an absolutely monstrous number of unconditional move instructions used to implement this C program. And sometime today, this is actually going to finish dumping out. And when it does, we'll be able to actually see this program run and run the program exactly as you would expect it to run. So this was sort of an exercise or a thought experiment in anti-reverse engineering or code obfuscation, but mostly I just thought it was funny. So when it's done, it'll actually run this program and it'll do all of AES using only move instructions. So I think it's a really cool, kind of neat tool. I would love to get some feedback on it. So I'd love it if people were interested in checking that out. So if you're interested in weird x86 things, I'll be talking a little bit more about that at DEF CON. But more importantly, at DEF CON, I wanted to illustrate another side project I've been working on. And that's a way of manipulating control flow graphs in assembly code. By manipulating your control flow graphs very carefully, I found that you could do really groundbreaking, revolutionary things like take a selfie in IDA. So I'll release some source code for doing that too. Check that out at DEF CON. If you're more interested in practical things, the Memory Sinkhole is practical, and you can find that source on GitHub as soon as I post that in about an hour. But I appreciate everyone's time here today. I think I'm out of time for questions, although I'm not sure about that. But if anyone wanted to talk to me about this offline, I would love to answer any questions or discuss this further. So thank you again.